Hey there, young geniuses. Here is some notes for 6.1. We have what's called an initial value problem right here. All that means is, here it says find the particular solution to this. A particular solution means we're going to find the function whose derivative is this. So it's an antiderivative problem. And the only difference is how we've been writing plus c. We're going to find the c value because we know a point that this thing passes through. So we're going to do, to find the antiderivative, we're going to set it up as an integral of e to the x minus 6x squared dx. The antiderivative, so this is going to be equal to our function y. Okay, because dy dx is this, so y is the antiderivative. The antiderivative is e to the x minus 2x cubed and then plus c. So that's our function for y. So we have y equals e to the x minus 2x squared, or 2x cubed, sorry, plus c. But then we know this point, 1, 0. So we can plug in 0 for y and 1 for x, giving us this, which allows us to solve for c, which is 2 minus e. Kind of a weird c value. A lot of times it just turns into a nice integer or whatever, but in this case it didn't, which is fine. And then all you do for your final answer is write your antiderivative. So I'm just rewriting the purple equation with my c plugged in, so plus 2 minus e. So this is, in fact, the function. That e looks really weird. So this is the function whose derivative is that. If you found the derivative of this, you would get this. And it passes through the point 1, 0. If you plug in 1 for x right here, you're going to get 0 for y. Okay, so that made those things true. When the problems we've been doing before, when we couldn't find the c value, those are called general solutions, as all B is talking about. And that's when you just have a plus c in your answer. You're not given an initial condition, is what that's called. Now, it's called an initial condition, but it doesn't have to occur at like t equals 0. It can be whenever. It just needs to be any point that you know is on the curve. All right, the infamous foot tattoo clip art. So fundamental theorem of calculus we're going to use on this one. So it's the same problem. We're given a derivative and a point that it goes through, and we're trying to find the original function. So again, f of x is going to equal the antiderivative of f prime. So I'm going to do e to the negative. Now I'm going to change this to a t right now, which you'll know why here in a second. The thing is, there's no antiderivative for this that we know. The antiderivative is not just simply e to the negative t squared, because if you do the derivative of this to check, it's e to the negative t squared times negative 2t, and this should be the same as that if this was the antiderivative. So it's not the antiderivative, so that doesn't work. And then there's no u sub that actually works either, because what most people will try is let u be negative t squared or just t squared, and then du is 2t dt. But since I have this extra t in here, that didn't look much like a t. Since I have this extra t right here, I can't just put a t in here and then divide by t out here. That only works with constants, not variables. So u sub doesn't actually work on this problem. So what happens is, this is already the antiderivative of this. Now that's the case when I make the upper bound an x. So if that's an x, remember, if I found the derivative of this, I just use this function because the derivative of an antiderivative, they cancel each other out. And then you just end up, in the antiderivative step, you would plug this bound in, so it gets plugged in. And so when you find the derivative, you just end up with that. That's exactly the fundamental theorem of calculus right here, saying that the derivative of an integral is equal to the function inside the integral with the upper bound plugged in. I know it's hard to see that. That's an x. I believe that's an a, meaning any constant. Because when the bottom bound is a constant, we don't need to worry about it. If they both have x in it, then you just do upper bound minus lower bound plugged in. So the derivative of that is, in fact, this. But the function also has to pass through the point 7, 3, which they gave us right here. So that was given. So how do we make this function pass through 7, 3? Well, notice how we haven't chosen a lower bound yet. And remember, our bounds are representing x values. So this part's kind of tricky, like what are we supposed to choose for our lower bound? And the answer is we're just going to choose this number, which does represent an x value. And the reason we're going to use that number is because when I plug in 7 for x, this 7 right here, for this x, I should get a y value of 3. But when I plug in 7 for x, this integral is easy to calculate. Because if I plug in 7 right here, I get the integral from 7 to 7, which is 0. So I've made this whole thing equal 0. Now that's not good because we want it to equal 3, but that's easy to adjust. Just put a plus 3 out here. And that's it. And that is because we don't know how to find the antiderivative, so we're kind of cheating a little bit and just writing the antiderivative as an integral. And then we just have we make it so that our bounds, when we plug in this x value, we get 0, so that we can just add this number at the end to get the y value we seek. So this function, f of x right here, does in fact have this derivative, because the derivative of an integral is just this plugged into there, basically. You know they can get more complex than that a little bit, but that's the gist of it. And then this, when you do the derivative, just goes away because it's a constant, so you get 0 from that derivative. And so we did find the function whose derivative is this that also passes through that point, using the fundamental theorem of calculus. All right, now we're going to construct a slope field. So what a slope field is we're going to find slopes at different points and then draw little tick marks to represent that slope at different points on the graph. So our derivative here is cosine of x. And we're going to find values of cosine at different values on unit circle that we know. So we have pi over 2, pi, 3 pi over 2, and 2 pi. And then this is negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi. All right, so let's just evaluate the cosine of 0. You should know that the cosine of 0 is equal to 1. So when x is 0, I'm going to put a slope of 1 like this, just everywhere x is 0, which is up and down that entire y-axis. It would go on forever, but we're only, going to draw it in what we see. And so those just have a slope of 1. It doesn't have to be perfect, but if you have a slope of 2 somewhere, you should draw it steeper than your slope of 1. Slopes of 0 are just going to be horizontal lines, and undefined slopes, keep them blank. Now, we don't get any undefined slopes here because cosine is never undefined, but it does happen in general. All right, so now let's find the cosine of plus or minus pi, because they're the same value, and that's negative 1. So at pi, I'm going to draw a slope of negative 1. In general, about the same steepness as my orange tick marks, because they both are 1, but this is negative. Okay, then we're going to do cosine of plus or minus pi over 2, which is 0, and 3 pi over 2 is also 0. So at all these places, I'm going to draw a slope of 0. I always draw them a little bit above the grid lines, because sometimes if it's on the grid line, it's hard to see, but it's a little easier these days with this technology and being able to choose different colors and stuff. But when it was a pencil on paper with gray grid lines, it was kind of difficult. All right, and then, so I have slopes of 0 everywhere there, and then we have cosine of plus or minus 2 pi is a value of 1 again. So now we have tick marks with a slope of 1, 1, 1, 1, 1, 1, 1, 1, 1. And then that's it. That's the slope field. We did the problem. It said construct a slope field for this. Done. Now I'm stressing that because then sometimes there's a second part to the question. If you're just constructing a slope field, you're done. That's it. This is it. Beautiful. But then sometimes there's this part where it says draw the solution curve that passes through, and then they'll just give you some random point. I've chosen 1, 0. So again, you don't always do what I'm about to do. You only do it when the question asks you to draw a solution curve. So here's the point 1, 0. What a solution curve needs to look like is it needs to look like the slope field. So if it passes through this point, it needs to have a slope of 1. Then as it approaches the pink, it has to go to a slope of 0. Then it's got to turn around and get a slope of negative 1, where the green is. Then it's got to turn back to a slope of 0, and then back to a slope of 1 like that. And so that's how, and it would go in both directions. So it would go this way like this. And it's got to like follow the slope field like that. Okay? Now, sometimes we recognize it better when it's only half of this graph drawn, but hopefully you recognize this as being the graph of sine, just shifted up. Well, it makes sense that the graph of sine, because what was the derivative? Cosine. So that's the usefulness of a slope field, is I could make this function right here anything I want. And you might not have any idea how to find the antiderivative, but you can construct a slope field for it, and you would know what the function actually looks like you would know its slope at different points. And the more slopes you find at, the more points you find it at, the more accurately you're going to be able to sketch the graph. So that's the idea of a slope field right there. And to reinforce this idea, this concept, you can Google electric field hockey, which if you do, so you get Google electric field hockey and then go to this first one right here, phet.colorado.edu. Click the play button. And this isn't going to be exactly like a slope field. This is an electric field, but it behaves very similarly. So you can kind of mess around with this. It's kind of fun. But see, we have a positive puck right here. And it says it at the bottom, puck is positive. And then click trace and field at the bottom. And what that's going to do is it's going to trace the path of your puck that it goes, and it's going to put the field lines on here, like the slope field, but it's going to be electric field. So you can pull charges out of these boxes, and when you let go, it draws the field for you. And so the field is the direction that the puck's going to go. So if I hit start, my goal is to shoot the puck into the blue goal over here, and it made it. Now, of course, that's very easy, but if you change your difficulty down here to 1, now it puts a wall in your way. So now we got to angle it this way, if it will let me grab that charge. There we go. Also, the intensity of the arrows is how fast the puck will move. So the darker the arrows, the more effect it's going to have. So if I hit start right now, you can see it's just going to follow the electric field lines, just like the slope field did. So that's not good. I need it to turn down there. So we can try like hit reset, not clear. Clear gets rid of all your charges. So maybe we try negative here and see how it changed the field completely. So now it's going to turn back. And, oh, it didn't quite do it enough. So now, I don't know, does that mean I need to move it like closer up here? But remember, every time you move it, it's changing multiple things. Oh, collision, that's so close. So you can mess around with this, though, and try to figure that out. And then there's 2 more difficulties, difficulty 2 and difficulty 3. You try to use as few charges as possible, but the point is to kind of learn how a slope field works. And that's it.